continue with this trip down memory lane, so hopefully these won't look too foreign to you. They look like should be things that you maybe have seen in previous classes, but just to sort of set the ground state for us. Here we have a certain hydrogen-like ion, A1 with only one electron. It emits light with a frequency that's given, and we're told that one associates that emitted photon of light uh, with the n equal to 2 to n equal to 1 transition. And then they want to know what will the frequency be for essentially the photon that makes the n equal to 3 to n equal to 2 transition for the same ion. Now we're not told what ion it is, but we are given some information. And this is a case where you could use that extended Rydberg formula for hydrogen and hydrogen-like ions, single electron ions that is given here. This is for a transition from M, the upper level M, to the lower level N state. Now we're not given the wavelength, but we can rapidly get this in terms of the frequency, and so I just use the speed of light as the wavelength times the frequency to solve for 1 over lambda, which is nu over c, the frequency over c, and I just made that substitution up above. And so the Rydberg formula could be rewritten in this form. And then I just write it out for the two transitions. I'm given this one, 2 to 1, so nu transition 2 to 1. And so the upper level is 2, the lower level is 1, always the lower level first. And then the third one, the transition from 3 down to 2, I can do likewise, write it down 3 to 2 over c, again using this general formula. And now the upper level is at 3 and transitioning down to n equal to 2. So I get, again, always the smaller of these two numbers goes first. And then I could do lots of complicated math on this, I suppose. But I just took the ratio of these two. In fact, I think I did 3 to 2. Yeah, I did. I said divide 3 to 2 over c by 2 to 1 over c. So basically I divided this whole equation by this top equation. On this side it becomes the frequency 3 to 2 on top divided by the 2 to 1. The c's will go out. And then that puts the 3 to 2 would be z squared r 1 over 2 squared minus 1 over 3 squared. And the 2 to 1, I put that in the denominator here, z squared r 1 over 1 squared minus 1 over 2 squared. And when I do that, then the unknown atomic number for this ion, z squared, goes out. In fact, the r goes out as well. And I can calculate that ratio. 2 squared is the fourth, 1 over 3 squared is the ninth, and then 1 minus 1 over 2 squared, which is a fourth, and when I did that I got 0.185. And so I know that the ratio is equal to this, and so nu 3,2 is just got to be 0.185 times nu 2 to 1. And I'm given that information. And when I multiplied it out on my calculator anyway, I got about 4.1 times 10 to the 15th hertz.